Greetings of day to all of you. I welcome all of my students to another lecture number 3 on flexible AC transmission systems, that's FACTS. In last couple of lectures, I have been discussing with you the main objective and main aim of using FACTS devices, FACTS controllers. The problems faced by largely interconnected power systems and the role of FACTS devices or role of FACTS technology in alleviating most of the problems faced by these interconnected transmission networks or interconnected power systems. In today's lecture, I am going to give you a brief classification or main classification of various types of FACTS controllers. I will write here basic types of FACTS controllers or FACTS devices. Basic types of FACTS controllers. Let us try to classify FACTS controllers into main categories, into different categories. Broadly, various types of FACTS devices or FACTS controllers are categorized as number 1, series FACTS controllers. Right here, series FACTS devices or series FACTS controllers. That is the first classification. Second classification is shunt FACTS controllers. Third classification is combined series FACTS controllers. Combined series FACTS controllers, and fourth is combined series shunt FACTS controllers. Combined series shunt FACTS combined series shunt FACTS controllers. So this is the main classification of various types of FACTS devices or various types of FACTS controllers. Series FACTS controllers, shunt FACTS controllers, combined series FACTS controllers, and combined series shunt FACTS controllers. Let us discuss them one by one in brief. First of all, I am going to discuss with you about series FACTS controllers, or what we call as series controllers. Well, a series controller actually behaves as a variable series impedance, okay, such as variable capacitance or variable inductance. I mean, when you connect a controller, FACTS controller, it behaves as a variable impedance, that is either variable capacitance or variable inductance in series with the line, or it also may behave as a power electronic source at either mains frequency or subsynchronous frequency or harmonic frequency as desired by your application. Okay, actually all these series FACTS controllers, they inject a voltage in series with a line. I mean, schematically, a series FACTS controller will look like this. This is the schematic diagram of a series FACTS controller. I have a transmission line. This is a long transmission line, and somewhere here I am connecting a series FACTS controller. Why is it called series FACTS controller? Because you can see it's connected in series with the transmission line, and it injects a voltage E like this. It injects a voltage E in series with the line. So that's what I have told you a few moments back, that all the series controllers inject a voltage in series with the transmission line, something like this. Now, what are the various types of series FACTS? This is the generalized diagram of a series FACTS controller. This is a FACTS controller. It injects a voltage in series with the line. It either behaves as a variable capacitance or a variable series inductance, or as a power electronic source, injecting a voltage E in series with the line. What are the various types of series FACTS controllers? The various types of series FACTS controllers are number 1, thyristor controlled series capacitor. Thyristor controlled series capacitor. This is also called TCSC. T for thyristor, C for controlled, S for series, and C for capacitor. TCSC, thyristor controlled series capacitor. This is the first type of series FACTS controller. Second is thyristor switched series capacitor. Thyristor switched series capacitor. So it is written as TSSC. In the literature, you will see that it is named as TSSC. That is thyristor switched series capacitor. The difference between thyristor controlled series capacitor TCSC and thyristor switched series capacitor TSSC is that in thyristor switched series capacitor only a few discrete capacitances are added in series with the line, whereas here the capacitance is continuously smoothly controlled. It is a variable capacitance in series with the line. Third type of series FACTS controller is thyristor controlled series reactor. Thyristor controlled series reactor. When I say reactor, it means inductive reactor. So TCSR, thyristor controlled series reactor. Fourth is thyristor switched series reactor. Thyristor switched series reactor. TSSR. Okay, so here these are thyristor controlled or thyristor switched series capacitors, and these two fall in the category of series reactors, variable reactors or series reactors which are thyristor controlled, right? And next is, or the last type is static synchronous series compensator. Static synchronous series compensator, which is also called SSSC, triple SC or S cube C. And last is static synchronous series capacitor or static synchronous series compensator with storage. That is SSSC with storage. Remember, we have whether it is a series FACTS controller or a shunt FACTS controller, these FACTS controllers are either thyristor controlled or they are converter based or converter controlled. As far as first four types of series FACTS controllers are concerned, thyristor controlled series capacitor TCSC, or thyristor switched series capacitor TSSC, or thyristor controlled series reactor TCSR, or thyristor switched series reactor TSSR. They are thyristor based series FACTS controllers. I will write here that they are thyristor based. And last two, that is static synchronous series compensator SSSC or SSSC with storage. They are converter based series FACTS controllers. I will write here converter, power converter based. They are converter based series FACTS controllers. So series FACTS controllers are either thyristor based or converter based. If they are thyristor based, they may be of four types: TCSC, TSSC, TCSR, or TSSR. And if they are converter based series controllers, they are of two types: SSSC or SSSC with storage. I will show you the schematic diagram of all of these series FACTS controllers. I mean schematically, or their schematic diagrams I will share with you. Let me first of all share with you the schematic diagram of thyristor controlled or thyristor switched series capacitor. So I have a capacitance which is in series with the line. This is my long high voltage transmission line. I have a capacitance in series with the line, capacitor bank of course. Then I make it a variable capacitance with the help of the thyristor, anti-parallel connected thyristors like this. These are SCRs. And then these SCRs are connected in series with the inductance. So when you do the firing angle or delay angle control of this thyristor, I mean, when voltage is positive, this thyristor is on, and when voltage is negative, this thyristor is on. So it is a bidirectional switch, thyristor based switch. It is in series with the inductance, and by delay angle or firing angle control of this bidirectional thyristor switch, this inductance, it varies, and it is in parallel with the capacitance, and it makes the series capacitance a variable parameter. It is either thyristor controlled series capacitor or thyristor switched series capacitor. So I will write here TCSC, thyristor controlled series capacitor, or the same schematic diagram holds true for thyristor switched series capacitor, TSSC. Okay. The next schematic diagram I will show for thyristor controlled series reactor, or thyristor switch series reactor. Again, this is a long high voltage power transmission line, and I have a thyristor based bidirectional switch like this, and in series with inductance. So again, by delay angle control of this thyristor switch, bidirectional switch, this inductance can be made variable. So it becomes thyristor controlled series reactor or thyristor switch series reactor, right? So therefore, this is schematic diagram for TCSC or TSSC, and this is the schematic diagram for TCSR or TSSR. That is about thyristor based series facts controllers. What about converter based series facts controller? Converter based series facts controller is like this. It is like this. This is the high voltage long transmission line. This is an injection transformer, and this injection transformer is connected like this. I have an IGBT based maybe 2-level or multi-level converter. So this is the schematic diagram of converter. This is a voltage source converter, and a voltage source converter has a DC link like this. So this is the schematic diagram of static synchronous series capacitor, static synchronous series compensator, SSSC. You can here see this is the converter. It converts DC into AC and injects a voltage in series with the line, and it becomes static synchronous series compensator, SSSC. So the voltage injected here in series with the line is E. Okay. Now this SSSC can be without storage or it can be with storage. This schematic diagram is for SSSC without storage, and with storage it will look like this. It will be like this. So again, this is the line, transmission line. This is the injection transformer, and I again have the same converter, IGBT. It may be GTO or IGBT based converter, power converter, maybe 2-level or multi-level converter. And then this is the DC link capacitance, CDC, with DC link voltage, VDC. And then I have a power electronics interface here. It may be a boost converter, DC to DC boost converter. So I will write here interface, or it may be a buck boost converter, interface. And then this is the storage. It may be either super magnetic energy, SMES, superconducting magnetic energy storage, or it may be a battery energy storage system. So in general, I will write here storage. So with storage, I already have some energy storage here, and then with the help of this power electronics interface, you maintain this DC voltage here constant, DC link voltage, and then this DC is converted into AC, and a variable voltage is injected in through this injection transformer in series with the line. So this becomes your SSSC with storage, which is a series facts controller, of course converter based, not thyristor based. So this is SSSC without storage, this is SSSC with storage. So that is all about series facts controllers. Now let us quickly move towards the shunt facts controllers. It's the second category of facts controllers. Don't worry, inshallah, in future lectures we will have to discuss all these series and shunt and other type of facts controllers one by one. I will take each facts device or facts controller, and I will try to explain the working operating principle, and we will analyze all these facts controllers. We will mathematically model them one by one in details, so that you can really appreciate their working and their role in interconnected power systems. So second category of facts controllers is shunt facts controllers. I will write here shunt controllers. Just like series controllers, shunt controllers also present a variable impedance, maybe either variable capacitance or variable inductance, or a variable source, or a combination of these. In principle, a series controller, I already told you, injects a voltage in series with the line, whereas a shunt controller, in principle, it injects a current at the point of connection into the line. It is something like this. Schematically, a shunt controller is shown like this. Let me show you. This is high voltage long transmission line. I am writing here line. Line means transmission line. And shunt controller may look like this schematically. It may be a thyristor based, or it may be converter based controller. And it injects a current I at the point of connection of the controller with the line. Whereas just few moments back you have seen a series controller is connected in series with the line, and that injects voltage in series with the line. Whereas shunt controller is connected in shunt or across the line, and it does not inject voltage. It injects the current at the point of connection with the line. So this is the schematic diagram of shunt controller. Now various types of shunt controllers or shunt facts controllers are like this. First is static wire compensator. Static wire compensator, which is also called SVC. Second type of shunt facts controller is static synchronous compensator. Static synchronous compensator, which is very popularly known as STATCOM. Some of you may have already come across this term at your BTech level, STATCOM. Maybe you have not studied it, or some of you may have briefly studied it. It's called static synchronous compensator, STATCOM. It is a shunt facts controller. Then we have static wire system, static wire generator, SVG, and we have thyristor controlled braking resistor, which is also a shunt controller. Thyristor controlled braking resistor, which is also written as TCBR, that is thyristor controlled braking resistor. So this is the main classification of shunt facts controllers. Let me draw a schematic diagram of all these types of shunt facts controllers one by one. The first type of shunt facts controller that I have written here is SVC, static wire compensator. Static wire compensator looks like this. We have a high voltage bus transmission line, and with the help of this transformer, it is a if you move in this direction, it is a step down transformer. If you move in this direction, it is a step up transformer. So with the help of this transformer, you are stepping down this high voltage into medium voltage, and you are creating medium voltage bus. And then to this medium voltage bus, you are connecting various components like this. Let me show various components. This is a thyristor bidirectional switch, anti-parallel connected thyristors or SCRs like this. This is called thyristor controlled reactor, TCR. And then we have another element like this. Again, two anti-parallel connected thyristors or bidirectional thyristor switch and a capacitor. This is called thyristor switched capacitor, TSC. This is TCR or TSR. You can call it thyristor controlled reactor or thyristor switched reactor. Okay, this is thyristor switched capacitor, TSC. And then you have a filter like this. You have an LC filter for removing the harmonics into the line. So this is filter. This is medium voltage bus. I should write it here. And then I may have a small inductor and I may have a small capacitor like this. Right? So this is the schematic diagram of static wire compensator, SVC. So SVC is basically a shunt facts controller. It's a shunt facts controller. You can see it's connected across the line. What we are doing, we are first of all transforming high voltage bus into medium voltage bus, because this high voltage bus may be at 132 kV or 200 kV or 400 kV, and our devices may not be available for such a high voltage rating. So what we are doing, we are stepping down the voltage and we are creating a medium voltage bus. And to this medium voltage bus, we are connecting various components of SVC. What are the various components of static wire compensator, SVC? First is thyristor control reactor or thyristor switched reactor, that's TCR or TSR. Second is thyristor switched capacitor, TSC. Then filter, and then this inductor and capacitor. These are various components of SVC. We will study in detail about SVC and its components in future lectures. So any amount of reactive power can be either injected into the bus or it can be absorbed from the bus as per the requirement. Sometimes, because of high reactive power demand of the load, reactive power may be required, and then that reactive power by this SVC is injected into the bus and supplied to the load. Or sometimes there may be excess reactive power available on the bus and that needs to be absorbed. In that case, this SVC will absorb the excess reactive power from the bus. We'll try to study it in details in future lectures. So this is a shunt facts controller, one of the shunt facts controllers, which is thyristor based shunt facts controller. It's called SVC, static wire compensator. So this is the schematic diagram of SVC. The other type of shunt facts controller is converter based shunt facts controller, and that's called STATCOM. So that looks like this. This is the high voltage transmission line. We have a parallel connected transformer like this, and then we have the converter. It may be a 2-level or a multi-level converter with DC bus like this. So this is called static synchronous compensator, STATCOM. This STATCOM is based on voltage source converter. I will write VSC based, that is voltage source converter based. Now we can see it has a DC bus, this inverter, this is basically an inverter. It converts DC into AC and it injects a current I into the line. So it acts as a shunt facts controller. Okay, so therefore it can either supply reactive power to the line, to the system, or it can absorb the reactive power from the line, from the system, depending upon the requirement. And here we don't have any thyristor controlled component, we have converter based system. This is a STATCOM is basically a shunt facts controller like SVC, but the difference being SVC is thyristor based shunt facts controller and STATCOM is converter based shunt facts controller. We can have STATCOM with storage like this. I will write again line. With storage I will show you. This is the block diagram of converter. This is the DC bus, and then we have interface, power electronics interface, and we have storage. It may be super magnetic energy system, it may be a super capacitor, or it may be battery bank storage. Now again, it injects a current into the line at the point of connection, and hence it can supply reactive power or it can absorb reactive power depending upon the requirement. Why this storage is provided? The main purpose of this storage is that in the event of fault on the system, if there is no power coming from here, then for a few cycles, for some time, the energy from the storage is taken by this converter, and that energy is converted from DC to AC form, and active power is supplied to the load during the outage, during the period of fault, during the period of outage for a few cycles, so that there is no interruption of power. Okay, here it can exchange only reactive power because it does not have storage. In this case, it can exchange reactive power as well as active power because of the presence of storage. So this is STATCOM with storage. Now STATCOM, this STATCOM is without storage and this is with storage, but both STATCOMs are based on voltage source converter, because if you see, this is the voltage source inverter or voltage source converter. This converter is also voltage source converter. We can have STATCOM based on current source converter also, and that will look like this. Again, we have a transformer and current source converter looks like this. So in current source converter, instead of having capacitance on the DC side, we have an inductor on the DC side. Okay, and instead of having this switch like this, we have switches like this, IGBT in series with diode, right? And then again current is injected into the system. So this is STATCOM, which is current source converter based, CSC, current source converter based. But let me tell you that voltage source converter based STATCOM is more popular in practice than current source converter based STATCOM. So that is about STATCOM. Now another type of shunt facts controller I have already discussed with you a few moments back is Thyristor controlled braking resistor. The Thyristor controlled braking resistor looks like this. We have a bus, and then we have thyristors or SCRs connected in anti-parallel, giving bidirectional thyristor switch, and then we have a fixed resistor. And by delay angle control of this switch, this R can be made a variable resistor, and then it can absorb any amount of power from the system and make the system more stable. We'll study about this. This is called Thyristor controlled braking resistor, TCBR. We'll study more about this TCBR in future lectures. So these are various types of shunt facts controllers. So we have studied series facts controllers, and we have studied about shunt facts controllers. Now let us discuss the hybrid, the combination of the two, that is combined series controllers and combined series shunt controllers. Third type of facts controllers are combined series controllers. I should write here combined series facts controllers, or simply we can say combined series controllers. Now these combined series controller may be consisting of two separate series controllers or a unified controller, as shown like this. I mean, we may have two series controllers. One controller is like this. This is the symbol of IGBT, symbol of GTO. And then another, this is one line. Another series controller is here. Okay, so what are these two? These two are lines, AC lines. I will write here AC lines. So in series with this AC line, we have one series controller, and in series with another parallel AC transmission line, we have another series controller. Now these series controllers are combined together, they are connected together, and they become a unified controller. Okay, so this is called a unified controller. It has a common DC power link. This is DC power link. Now this series controller, it supplies the reactive power to both the lines, and also real power. Real power it supplies via DC power link. I mean, the real power can flow from this controller, from this line to this line via this DC power link, or real power may flow from this line to this line via same DC power link. Okay, sometimes what happens, this line may be underloaded and this line may be overloaded. So therefore we want to shift some of the power from this overloaded line to underutilized line. So in that case, the power will flow from this controller through this controller via this DC link to this. So there is the shifting of power. Or if this line is overloaded and this line is underloaded, okay, in that case some of the power we may like to shift. I mean, this is underloaded and this is overloaded. We may try to shift some power from this line to this line. Okay, so therefore through this DC power link, power can be exchanged. Power can be shifted from this line to this line, or this line to this line, vice versa. So this balances the active and reactive power, thus enhancing the capability of transmission lines for power transfer. Okay, this is called interline power flow controller also. This type of facts controller, combined series facts controller, is also called interline power flow controller, IPFC. Interline power flow controller, IPFC. We will study about interline power flow controller in future lectures, maybe after midterm examination. Okay, so this is about combined series controller. So actually I will again repeat. I will repeat. Combined series controller comprises of two series controllers which act as a unified controller like this. They supply the active power as reactive power, and they exchange the active power via DC power link. So therefore they balance both active as well as reactive power of the two these parallel connected transmission lines, and hence they increase the power transfer capability of both the transmission lines. This type of series controller is also called interline power flow controller, IPFC. And then last type of controller is called combined series shunt controller. Combined series shunt controllers. That means one of the facts controller is series connected, and another facts controller is shunt connected. That's why it's called combined series shunt controller. It may be a combination of separate series and shunt controllers with a coordinated control like this. I mean, it may be something like this. Try to understand. I have a series facts controller like this. This is series facts controller. This is my transmission line. These are the two buses. And I have a shunt facts controller like this. This is the shunt facts controller like this, and I have a coordinated control. This block results in coordinated control of two controllers, that's series and shunt controllers. Coordinated control scheme or coordinated controller. Okay, this is not SCR, this is GTO. See, SCR has this symbol and GTO has this symbol. GTO is actually used for high voltage and high power applications, since we are connecting these devices to high power, high voltage transmission lines. So you can either use IGBTs or GTOs. I am showing GTO based controllers. So this is a shunt connected facts controller. It injects a current I at the point of connection, and this is a series connected facts controller. It injects a voltage E in series with the transmission line, right? So these are two separate controllers, series controller, shunt controller, and they are controlled in a coordinated manner like this. Or it can be a unified power flow controller. In case of a unified power flow controller, the two controllers, series and shunt controllers, are considered as a single unit, and they are controlled, as a single unit in a unified manner like this. Let me show you. So this is series controller injecting a voltage E in series with the line. This is the line. Okay, and we have a shunt controller also. This is a shunt connected controller. It injects a current I. There are transformers also here, maybe injection transformer here, also a coupling transformer. I am not showing those details. When we study these controllers, I will show the complete circuit diagram, schematic diagram, along with the whereby I will show the transformer connections also. Here, this is the generalized block diagram or schematic diagram. Okay, so this is the common DC link, DC power link. Okay, this is shunt controller, this series controller, common DC power link, and we may have a storage also. It depends whether you require a storage or not. It may be with storage. Okay, so with transformers, it looks like this. We have a coupling transformer for shunt controller like this, and this is the diagram for shunt controller. This is GTO, and this is anti-parallel connected diode. So this is basically a converter, and another converter we have here with injection transformer like this. Again, we have a converter comprising of IGBT or GTO switches with anti-parallel connected diodes like this. and we have a common DC bus. If you remember in power quality problems and solutions course, we have studied UPQC, Unified Power Quality Conditioner. It also looks like a unified power quality conditioner. Okay, this is the line. A unified power quality conditioner UPQC comprises of shunt controller and series controller. There, as a custom power device, the shunt controller is called DStatCom and series controller is called DVR. In transmission line applications, the same combination is called unified power flow controller. It's not called unified power quality conditioner, it is called unified power flow controller. Unified power flow controller, UPFC. UPFC. And this unified power flow controller comprises of a shunt controller, which is basically a converter based controller which injects a current I at the point of connection through this coupling transformer, and it comprises of a series controller, FACTS controller like this, which is this, and it injects a voltage E in series with this line through this injection transformer, and they have a common DC bus like this. So this is the schematic diagram of UPFC, which is basically a combination of shunt controller and series controller. We will try to study this in details about UPFC in one of the future lectures. Okay, so this is about combined series shunt controller, or UPFC, Unified Power Flow Controller. So additionally, we have more controllers. I will write here. Additionally, we have more controllers, like we have Thyristor controlled voltage regulator. Let me first of all draw its schematic diagram. This is three-phase system, and we are tapping energy from two phases like this. This is the transformer primary, and this is the transformer secondary, which is connected to a converter, IGBT or GTO based converter like this. And this is our injection transformer primary, and this is injection transformer secondary. This is called Thyristor controlled voltage regulator. Thyristor controlled voltage regulator. Sorry, Thyristor controlled phase shifting transformer. Thyristor controlled phase shifting. I'm sorry, it's not voltage controller, it is phase shifting transformer. Thyristor controlled phase shifting transformer, which is also called TCPSR. Thyristor controlled TCPST. Thyristor controlled phase shifting transformer. With the help of this arrangement, we can change the phase angle of a particular transmission line between the buses, between this bus, sending bus, and the receiving bus, and we can control the flow of power. So this is the schematic diagram of Thyristor controlled phase shifting transformer. We will study about it in future. And then we can have Thyristor controlled voltage regulator also. I mean, we can have a Thyristor controlled voltage regulator like this. This is a GTO along with anti-parallel connected diode. This is transformer primary. Sorry, this is transformer primary, and this is the transformer secondary, and this is our transmission line. This is Thyristor controlled voltage regulator. This is not Thyristor controlled phase shifting transformer. This is Thyristor controlled voltage regulator. Voltage regulator, which is also called TCVR. VR means voltage regulator, based on voltage injection. Based on voltage injection. Why is it based on voltage injection? Because we are injecting certain amount of voltage in series with the line, and hence we are regulating bus voltage. I mean, we want to regulate the voltage of this line. We can regulate it with the help of this, right? So then we can have Thyristor controlled voltage regulator based on tap changing transformer. So that will look like this. Let me show you the schematic diagram. That will look like this. This is thyristor. This is the schematic diagram of thyristor controlled voltage regulator based on transformer tap changing. Based on tap changing. Depending upon which switch is on, we can have different taps. We can go for tap changing. I mean, we can bypass this tap and use only these two taps, or we can bypass this and this tap, use only this tap, or we can use all the three taps or any one of them, and we can have more number of taps. Depending upon the tap changing, the output voltage can be regulated. So this is also a type of thyristor controlled voltage regulator, TCVR, but it is not based on voltage injection. It is based on tap changing. We'll study about it in future classes. So that is all about various types of FACTS controllers. Summarizing, I have discussed with you thyristor controlled, these series FACTS controllers. And I told you that a series FACTS controller basically provides or produces a variable impedance or variable inductance or variable capacitance or variable power source in series with the line. Fundamentally, a series controllers actually inject a voltage in series with the line. And then we discussed that these series FACTS controllers are of different types, like thyristor controlled series capacitor, TCSC, thyristor switch series capacitor, TSSC, thyristor controlled series reactor, TCSR, thyristor switch series reactor, TSSR, which are thyristor based. And the series controller, which is converter based, is static series synchronous compensator, SSSC, or SSSC with storage. Okay, and then we discussed various types of these shunt FACTS controllers. I told you that just like series FACTS controllers, shunt FACTS controllers also may behave as variable impedance or variable source or a combination of these, and they fundamentally inject current at the point of connection into the transmission line, and hence they exchange mostly reactive power with the line and sometimes active power also, depending upon whether storage is there or not. Then they are classified into static wire compensator, SVC, which is thyristor based shunt FACTS controller, or static synchronous compensator, STATCOM without storage and STATCOM with storage, voltage source converter based STATCOM, current source converter based STATCOM. We have also discussed actually STATCOM is converter based shunt FACTS controller, while SVC is thyristor based shunt FACTS controller. I have also discussed with you thyristor controlled braking resistor, TCBR. Okay, and then we discussed combined series controller, interline power flow controller, which comprises of two series connected FACTS controllers which exchange, which control the active power, reactive power. They actually exchange active power via common DC power link, and they control the reactive power of the lines and hence enhancing their power transfer capabilities. Then I discussed with you combined series shunt controller, which is also called unified power flow controller, UPFC, which comprises of a series FACTS controller which injects a voltage in series with the line, and shunt FACTS controller which injects current at the point of connection. And these two controllers have common DC bus, and they can balance, they can control both active as well as reactive power of the line. And then I discussed with you additionally thyristor controlled phase shifting transformer, thyristor controlled voltage regulator based on voltage injection, and thyristor controlled voltage regulator based on transformer tap changing. So these are various categories of FACTS controllers. Most of these FACTS controllers, or all of these FACTS controllers that I have, whose classification I have given you today, which may be either series FACTS controllers or shunt FACTS controllers, or combined series controller, or combined series shunt controller, or TC PST or TCVR. We will discuss almost all of them in details in future classes. Okay. So let me tabulate various types of series and shunt and other type of FACTS controllers and discuss with you their control attributes. I will have two column table. First column is FACTS controller or FACTS device, and second column is its control attributes. Control attributes. So first of all, I will discuss with you series FACTS controllers. Series FACTS controllers, I have thyristor controlled series capacitor or thyristor switched series capacitor. which is Thyristor based series capacitor. Its control attributes are current control. It controls the current control, then voltage stability, then dynamic and transient stability. I should write transient stability, damping oscillations, and fault current limiting. If you see the series facts controller like TCSC or TSSC, that is Thyristor controlled series capacitor or Thyristor switch series capacitor, this is its control attributes. It can result in current control in the transmission lines. It can improve the voltage stability of the line. It can improve the transient stability of the line. We'll see that in future classes. It can result in damping of power oscillations or electromechanical oscillations, and it can also limit the fault current. It can be used for fault current limiting. So these are its control attributes. Second is Thyristor controlled series reactor or Thyristor switch series reactor. Its control attributes are same. It does the same functions, same jobs as done by TCSC or TSSC. So its control attributes do not change. They are same, like current control, voltage stability, transient stability, improvement, damping oscillations, and fault current limiting. Okay, so these are Thyristor based series compensators or series controllers. What about converter based series controller, that is SSSC, static series synchronous compensator? First of all, we will have without storage. If you have converter based series facts controller, which is also called SSSC, its control attributes are same: current control, voltage stability, transient stability improvement, damping oscillations. So same attributes, right? And then you have SSSC with storage. It will also have same control attributes. So whether you use TCSC or TSSC, TCSR or TSSR, or SSSC without storage or SSSC with storage, these are different types of series facts controllers, but their control attributes are almost common. Same control attributes are there, right? So now let us quickly go to shunt facts controllers and discuss their or list their control attributes. Now, first type of shunt facts controller is static wire compensator, SVC. What are its control attributes? It can result in voltage control. This is its first control attribute, that is voltage control. Then it will result in voltage stability. It will provide voltage support to the bus and hence result in voltage stability. Damping of power oscillations or damping of electromechanical oscillations. I will write here damping power oscillations. This is its other control attribute. Transient stability improvement. And wear compensation. That wear means reactive power. Within brackets I can write Q compensation. That is reactive power compensation. These are various control attributes of shunt facts, Thyristor based shunt facts controller, which is called static wire compensator, SVC. And then converter based shunt facts controller is called STATCOM. I will write now here static synchronous compensator or STATCOM. First of all, I will take STATCOM without storage. A STATCOM which does not have storage. It has same control attributes as SVC. Okay. Then I have STATCOM with storage. STATCOM with storage. With storage, it has all the control attributes as STATCOM without storage, I have written here ditto plus active power injection for some cycles, plus active power injection for some cycles, for a few cycles during the fault condition. STATCOM without storage has all these control attributes, but it cannot, supply the active power. But STATCOM with storage has all these control attributes, plus it can supply active power, or it can inject active power for a few cycles, for some cycles. Okay, so that is this. And then we have another shunt factors controller, thyristor controlled braking resistor, TCBR. TCBR has these control attributes. It results in transient stability improvement. I will write here, it improves the transient stability of the system, and it also helps in damping oscillations. Damping oscillations, power oscillations, or electromechanical oscillation. It cannot provide voltage control, it cannot provide voltage stability, right? It cannot provide reactive power compensation. It can provide only, it has only two control attributes. It's used to improve the transient stability of power transmission system, and also damping power oscillations. I should write here power oscillations. It helps in quick damping of power oscillations, right? So that is about shunt factors controllers. Now after this we have combined series controllers, and then combined series shunt controllers. Let us discuss their, or let me list their control attributes. So first of all, I will write combined series controller, which is interline power flow controller, IPFC. What are its control attributes? It is a combined series controller. Its control attributes are like this: reactive power control, that is Q control, the reactive power control, comma, damping power oscillations, or I should write damping oscillations, right? Then improving the transient stability of the system, transient stability. Then voltage control, it also provides voltage control, and it also provides voltage stability. Voltage stability. So these are the control attributes of combined series factors controller, which is interline power flow controller, IPFC. And then we have combined series shunt factors controller, which is also called unified power flow controller, UPFC, which comprises of a series factors controller and a shunt factors controller. UPFC, unified power flow controller. What are its control attributes? Its control attributes are same as those of interline power flow controller, ditto, do. Okay, and then we have additional controllers, that is thyristor controlled phase shifting transformer, TCPST. What are its control attributes? When you are changing the phase shift, when you are changing the phase angle of a power transmission line, you are actually controlling the active power. So I will write active power control. It results in active power control. It results in voltage stability. This is its next control attribute. It helps in damping of power oscillations, and it helps in improvement of dynamic and transient stability. It improves transient stability of the system. So these are the control attributes of TCPST, that's thyristor controlled phase shift transformer. Then we have thyristor controlled voltage regulator, TCVR. What are its control attributes? Thyristor controlled phase shifting transformer controls the active power, whereas thyristor controlled voltage regulator controls reactive power. Okay, it cannot control active power, but it controls reactive power. I will write here reactive power control. And then all other attributes remain same, that is voltage control, voltage stability, damping of power oscillations, right? And then improvement of transient stability. So these are the control attributes of TCVR, TCPST and TCVR have almost same control attributes, except for that is Thyristor control phase shifting transformer. TCPST controls active power, whereas Thyristor control voltage regulator. TCVR controls reactive power. Okay, so that is about different types of series, shunt, combined series, series and combined series, shunt, and phase shifting and voltage regulator type of these FACTS controllers and their control attributes. Fine. So with this background knowledge about the classification of various types of FACTS controllers and their control attributes, we can now start studying these FACTS devices one by one. We can first start with series FACTS controllers, then shunt FACTS controllers, and we can go step by step and study all of these FACTS devices one by one. But before we do that, let me summarize what are the various benefits from FACTS technology. I will write here benefits from FACTS technology. What benefits do we have when we use FACTS technology? What are the benefits from FACTS technology? First benefit is control of power flow. Control of power flow. I mean, you have seen whether we use series FACTS controller or shunt FACTS controller or IPFC or UPFC or Thyristor control phase shifting transformer, we can using these various types of FACTS devices, we can have perfect control over active power. So control of power flow can be achieved. Okay. Second is increasing loadability or loading capability, increasing loading capability of a power transmission line, lines to their thermal limits, As you already know, AC power transmission lines cannot be loaded up to their thermal limits because of stability issue, which we have discussed in details in HVDC power transmission systems, HVDC systems, which was one of the courses in our MTech second semester, last semester, spring 2021. Now, because the power angle, maximum power angle that you can have is 20 to 25 degrees, whereas maximum power transfer capability takes place at delta equal to 90 degrees, but you can never operate a transmission system at delta equal to 90 degrees due to stability issues. So you have to operate it at a much lower delta, much lower transmission angle, about 25 to 30 degrees, and therefore you are not able to fully load the transmission line up to its thermal limit. So however, with the help of FACTS technology, you can increase the power handling or power transfer capability of an existing transmission network up to its thermal limit. Okay, so there is no limit to this loading capability of transmission line. You can fully load a power transmission line up to its thermal limit. So this is another benefit that we get from FACTS technology. Third is reducing reactive power flowing on the transmission line, reducing reactive power, thus allowing the line to carry more active power, thus allowing the line to carry more active power. Because using FACTS controller, whether it is a series FACTS controller or shunt FACTS controller or combined series FACTS controller like IPFC or combined series shunt or FACTS controller like UPFC, with the help of these FACTS devices, you can control or you can reduce the reactive power flowing on the line. And hence, when reactive power flow on the line is reduced, the same line can carry more active power and can carry more megawatts and supply more power to the load. So therefore, by using FACTS devices, reactive power flow over the lines can be reduced, thus allowing the line to carry more active power. So this is another advantage of or another benefit from FACTS technology. The next advantage is providing voltage support. at system buses, providing voltage support at system buses. Sometimes what happens, due to some huge reactive power flow or due to some fault, a particular bus may collapse. I mean, the voltage at a particular bus may collapse. But if you have a FACTS controller connected there or near to that bus, that FACTS controller will immediately provide the voltage support to that particular system bus, and hence it will avoid voltage collapse at that particular bus. Okay, so this is another advantage of FACTS technology. Okay. Next is increasing system security. Increasing system security by way of improving transient stability of the transmission system, by way of improving transient stability limit of the system, limiting short circuit currents, limiting SC means short circuit currents, and damping electromechanical or power oscillations, and damping electromechanical oscillations, in power systems. You know what, the beauty of FACTS controllers or FACTS technology is that it makes your interconnected power transmission network very secure. How? By improving its transient stability limit. So it makes it more stable by increasing its transient stability limit, limiting the magnitude of short circuit currents in the event of a short circuit or a fault, and quickly damping the electromechanical oscillations. And hence that way it makes the power system very much secure. Okay, and finally, providing or provision of secure tie line connection to neighboring utilities, and regions. I mean, you can connect two different regions together, you can connect the utilities together, and when you are connecting them, you are interconnecting them, you are ensuring the security of the interconnected systems. So what FACTS technology will do, it will provide secure tie line connections to neighboring utilities and neighboring regions. So these are the main benefits or main advantages of using FACTS technology. That means with the help of FACTS technology, we can exercise complete control of power flow over various transmission lines, thereby avoiding the possibility of overloading of the lines, parallel transmission lines. We can also increase the loading capability of transmission lines to their thermal limits. We can also reduce reactive power on a particular transmission line, thus allowing more active power to flow over it. We can also provide voltage support at system bus using FACTS technology. With the help of FACTS technology, the system becomes more secure by way of improving its transient stability limit, limiting the short circuit current magnitudes, and quickly damping electromechanical oscillations. And finally, it provides secure tie line connections to neighboring utilities and regions. So these are some of the main benefits from FACTS technology. It is because of these benefits that in largely interconnected power transmission networks, the demand of FACTS technology is growing day by day. So that's all about today's lecture. So in today's lecture, I have discussed with you, I have given you the broad classification of various types of FACTS devices or FACTS controllers, their control attributes, and what are the benefits we can have from FACTS technology. I advise all of you to go through this lecture and other earlier lectures, and in case of any doubts, Please put your queries on YouTube channel or on WhatsApp group. I wish all the best to all of you. Thank you.